Okay, so in this class we'll learn to apply the Bohr-Berry rules, the 4 Bohr-Berry rules that we wrote in the previous class. Okay, so we will now learn how to practically apply them into specific atoms. Okay, so for that, take your pen and scale. Okay, pen and scale, and do like me. On your copy, you make a margin for columns and rows. Okay, for columns and rows. Full page is going to be good to get more space. So let us say in this first column we have the elements. So you draw like that, and here write the elements. We're going to apply the Bohr-Berry rule for the first 20 elements and the noble gases. Don't bother too much about what noble gases mean now. Just follow, you'll get it. Then here draw another line, and here write the symbol of the elements. So we're going to learn some important symbols as well. Then okay, you can make a margin here if you want. Okay, so here symbols of the elements. Then in the next one, atomic number. So make a margin. Okay, atomic number. So we will get to understand what is meant by atomic number also through practical application, so it becomes easy. Then we have here number of protons. So just write here number of protons. So now we're learning the 3 atomic particles are protons, the next electrons, neutrons. So we're going to do that, number of protons, then number of neutrons. So next one is the number of neutrons. Number of neutrons, then number of electrons. So here, number of electrons. So the 3 particles found in any atom are protons, neutrons, and electrons. Keep that in mind. Okay. Then we're going to see Bohr-Berry rule, especially to find out how the electrons are arranged. Okay, we don't need Bohr-Berry rule to arrange protons and neutrons. Okay, we will learn as we go on. So we're going to find out how these electrons are going to be arranged by using Bohr-Berry rule. So arrangement of electrons in distribution of electrons. So here, the last row except the last row, here you draw a line and you write here another line. Then you write here distribution of electrons. Distribution. Okay, distribution of electrons in the different orbits. So let me just tell you here, protons and neutrons are stationary and they're found in the middle of the atom. Protons and neutrons never move in the middle position. And electrons are arranged in orbits, means circular paths. First orbit, second orbit. And electrons are never stationary, they are revolving, moving in the orbits. Protons and neutrons are in the nucleus, center part is called nucleus. Electrons are moving in orbits, so that's what we're going to do. So we're going to see how they are arranged in orbits. So the number of shells, 4 of them is enough, I think. So here we have K, L, M, N. So okay, 4 shells is enough, I think. K, L, M, N, O, P. Okay, K, L, M, N, O, P. Okay, K. First shell is called number 1 or K, L or 2, MO3, NO4, 5, KLMN, KLMNOB. So K or number 1 orbit, okay, you can write 1 if you want, L or number 2 orbit. You need not use both, 1 is enough. M or number 3 orbit is called M, N or 4, O or 5, P or 6. So first shell is called K, second, third, fourth, fifth, sixth, seventh, later they can go, but we need only up to 6 I think for our purpose. So here K, L, M, N, O, P simply means K is first orbit, L is second orbit, M is third orbit, like that, okay. So next, the last one, we're going to learn a term called valency also. So as we do this, we will understand these terms. Valency, distribution of electrons, means electronic configuration, meaning same. Electrons, neutrons, protons, atomic number, symbols, and the elements. So we're going to learn these things in a practical way by doing this activity. So keep this as an activity, okay, and write all these things and draw these margins using pen, okay, and scale. Now let us go here. The first 10 elements let's do in this class. Okay, so here 1. Okay, I think I can use my freehand. 1, 2, 3, 4, 5, 6, 7, 8. Okay, I took a little bit of more space. 2. Okay, so here I think we can make it 2 here. Wait. A little bit of down. Sorry. So here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So let's do with this. This is fine. Okay, so here 10. So the first 20 elements we're going to do in this class as we start the activity. Okay, you can continue to draw down and make it 20 later on. For me, I don't have space. The first element, the simplest element and the lowest element is called hydrogen. There is no element smaller than this or simpler than this. There are 116 elements known to us presently, I think. And hydrogen is the lightest element or the smallest element. So we start with the smallest. Its symbol is given by capital H. The first letter of the English name hydrogen is used as its symbol. Symbol means short form. Lowest, so atomic number is 1. Okay. Then the second one is called helium. Just write along with me. Helium. Okay, helium. Okay, let me write like this so that we can understand it. Now, I forgot to tell you, but writing these things you write with pen, okay? So just now, pen. So here, everything pen. So here, the first element is called hydrogen. Let me write in small letters. Then the second one is a noble gas. Wherever it's noble gas, I'm going to put asterisk and capital letter. The simplest noble gas. There are 6 noble gases. The others are not noble, only this is noble. Okay, so the symbol is the first 2 letters, H and E. And we know in symbols, the uppercase, the first letter is always capital and the second letter is always small. Lowercase, second letter. So 2. So we can write these things. So 3, 4, 5, 6, 7, 8, atomic number 9, 10. The first 10 simplest elements, they will be in serial. So the third element is called lithium. Lithium, right? All these things. Symbol is L, capital, small I. First 2 letters. Lithium, beryllium. The next one is beryllium. B-E-R-Y. L-I-U-M. L-I-U-M. And it is denoted by the symbol B. Okay. And small e, the first 2 letters. atomic number is 4. Okay, then here, beryllium, boron, carbon, nitrogen. Boron, all these are not noble, capital B. Boron, carbon, symbol is capital C. Nitrogen, oxygen, so nitrogen, capital N. Oxygen, capital O. The next element, and the next one, fluorine, F-L-U-O-R-I-N-E, capital F. And then the next noble gas is the neon. So here you write neon in capital letters, and asterisk means this is the second noble gas, N-E-O-N. And the symbol for neon is the first two letters, N capital, first uppercase, lowercase, second letter small, N-E. And it has atomic number 10. So there are two noble gases appearing in our first activity, helium and neon. The others are all not noble gases. So just write it with pen, all these things also. Now take your pencil and follow me this activity. We are going to learn Bohr-Berry rule, how to apply it. Now before we go to Bohr-Berry, we'll start applying in this section. Okay, arrangement of electrons is what Bohr-Berry rule is going to help us to do, but arrangement of protons, neutrons, these things, we don't need Bohr-Berry rules here. What is atomic number? May I explain that to you? Atomic number, if you want to write down. Okay, atomic number, you can write on a new page if you want. Okay, no need to write, just look at atomic number is the number of protons or number of electrons. I repeat, the number of protons or number of electrons, not put together, okay? Number of protons or number of electrons in any atom is called its atomic number. That means atomic number is the number of protons. Number of protons is atomic number, and number of electrons. Okay, let me say the actual definition of atomic number is the number of protons found in any atom. So in hydrogen atom, atomic number is 1 means number of proton is 1. In helium, atomic number is 2 means number of protons is 2. So basically, these things you write with pencil, okay, now. So you can wrap it out and do your own activity again and again. So from here up to here, everything else is pen, writing margin also, drawing margins, and then writing these things from here to here, all this pencil. So once we complete this activity also, you can understand, wrap it out and apply it 3, 4, 5 times, redo it to understand properly, you can do that. So this is an activity table. Now atomic number, I repeat, is the number of protons in an atom, that's all. So atomic number of lithium is 3 means number of protons is 3. 4, beryllium, atomic number is 4 means number of protons is 4. So likewise, number of protons in the rest will be the same as the atomic number, because atomic number is simply the number of protons. And I want us to go here, skip this one and go here with pencil everywhere. From now, pencil from here to here, use pencil. So you can rub it out with your eraser and keep on repeating it till you understand it or get a good grasp of the concept. Okay, so here, number of neutrons, leave it for now. Now, here, mass number is not mentioned, but let me just tell that. Atomic number is the number of protons. This is the correct definition. But incidentally, in every atom, number of protons is always equal to number of electrons. Any atom you take, all the 116 elements that you know, the atoms of those 106 elements, all of them have the same behavior, that the number of protons and number of electrons are always equal to each other. So if there is 1 proton in hydrogen atom, there will be 1 electron. 2 protons in helium means there will be 2 electrons in. So it's same. So you can write down. So number of protons and electrons in any atom are always equal. In other words, neon has got 10 protons, but it has only 8 electrons, impossible. They will be always equal, number of protons and electrons. Keep that in mind. Then you can write down this one in the next page of your notebook. Atomic number is mentioned in our activity, but atomic mass, mass number. What is mass number? Look here, mass number. Mass number is simply number of protons plus neutrons together is called mass number. Keep that in mind. Okay, protons and neutrons. Now in our activity you can write this one with pencil, and everything here pencil, but this one you can write it with pen. Let me just give it to you. So here the simplest element, hydrogen, has no neutron. Okay, so we're learning something important here today. The only element known to us which has no neutrons in the nucleus is hydrogen. The rest all have neutrons. Then helium has got 2 neutrons. Just memorize, write these things with your pen. This pencil. This one you can write with pen. So 2, 4, 5. So 4. Lithium has got 4 neutrons. Beryllium 5 neutrons. Boron has got 6 neutrons. And carbon also has got 6 neutrons. Okay, and then nitrogen has 7 neutrons. Oxygen, fluorine, 8 and 10. So 8 neutrons. Fluorine 8. Sorry, 8. Oxygen has got 8. Fluorine and neon has 10. Fluorine has 10 neutrons. Neon also has 10 neutrons. This is something that you just write with pen for your information. Okay, now we're going to apply the Bohr-Bury rule. So Bohr-Bury rule tells us how electrons are arranged. So hydrogen has only 1 electron. See here, 1 electron. So the first rule says the electrons must first fill the lowest energy level, means we should fill up K full first shell. Then if its K shell is not sufficient, then only we put the extra electrons in the second. What this rule 1 is saying is that we should not start filling the second and go to first, or start filling from the 6th shell and go inside, but always start from inside lowest orbit and go to the outer orbits. Meaning, if all the electrons can go in the first orbit, let it be so. And if we don't need second orbit, leave it like that. But we should not put electrons first in the next orbit and come back here. So we should start from K, then go to L. Not sufficient, go to M. Not sufficient, then go to N. Okay, so here it has got 1 electron, means the number of electrons that can go in any orbit is 2n square. And we know, no need to write it. First orbit, we know in our previous class we learned maximum 2 electrons can go. Second orbit, 8 electrons, right? And the third orbit, 18 electrons. So since according to rule number 2, maximum number given by 2n square, first orbit has maximum 2 electrons and hydrogen has only 1 electron, it can easily accommodate here and we don't need the second. So this is the arrangement. Now let us go to the next, and valency we'll discuss last. Okay, so here helium has got 2 electrons and the maximum number of electrons that can go into first K shell is 2. So perfectly fitting 2. So that is why it is called noble gas. Hydrogen is not noble gas because maximum in the first shell can go is 2 electrons, but it has only 1 electron, so it has 1 less to become perfect fill, means maximum fill. That's why it's not a perfect element. That's why it's not noble. Noble means arrangement of electron is perfect up to the maximum. Okay, so this is the first noble gas. And then go to the third. Here 3 electrons. So first shell can have 2 electrons, so I put in the K shell 2 electrons. But since lithium has 3 electrons, 1 is still left, 3 minus 2, 1. That I should not put here. After filling, I know that maximum in the first orbit K is 2, so I cannot put more. Like this, forcefully push inside 3 is not possible. So maximum allowed rule is 2. So the extra one, I use the next orbit like this, L. So lithium electron arrangement is first orbit 2 electrons, second orbit 1 electron. So it's not perfect because second orbit here, second orbit 8. To become perfect, it needs 7 more. 7 plus 1, 8. So it's not perfect, so it's not noble. Okay, I hope you're getting it. Then beryllium, maximum number of electrons is 4. So according to rule number 2, maximum number of electrons according to 2n square rule is second orbit, first orbit is 2. So I put there 2. But 4 minus 2, 2 still left. I can't put in first, so go to the next. Not perfect. You need 6 more. 6 plus 2, 8 to become second orbit perfect is 8. so it's not noble. Next, boron has got 5. So according to the rule number 2, first shell 2, second shell or orbit is 8, but 5 minus 2 is 3 only, so I put here 3. So not perfect. It needs 5 more. 3 plus 5 then only will come 8. So it's not perfect. So it's therefore it's not noble element. Carbon. So only 6 noble elements are there in out of 116. Okay, that means only 6 elements have perfect electron arrangements. The rest are imperfect. Okay. So carbon here is 6. So the maximum in the first orbit is 2. Then second orbit maximum is 8. But 6 minus 2 is 4. So less than the maximum is easily can go. What we mean is, if in a bench in a class 4 student maximum can sit, then we cannot put 5, right? But we can easily put less than maximum. So 4 maximum means 2 students can be put easily. So less than maximum 8, 4 easily. So 4 plus 2, 6. Right, next one likewise. First orbit 7 electrons means 2, 5 here, 5 plus 2. So allowed because second not yet cross 8. So we don't need third shell. Next one, oxygen is 8, so 2 plus 6 allowed because still below 8. So 2 plus 6, 8. Then 2 plus 7, 9 electrons. So the 9 electrons will be arranged in such the first shell 2 electrons, second orbit 7 electrons, 4 fluorine, and 10 here. So 2 and 10 minus 2 is still 8 is there, perfectly fit into the second orbit 8. See, second orbit perfect maximum is 8, 2, 8. So this element neon has perfect arrangement up to the maximum 8 in the second shell. First shell maximum 2 and fitting. Second also maximum 8. Exactly fitting 8 plus 2, 10. That's why it's called a perfect element or noble element or royal element also we call it. Okay. So we have 2 noble elements here. So I'm going to now explain valency to us. Okay, valency. We're going to learn that by doing this activity. As I said, write everything, draw everything by pen. These rolls of pen. Then this one, protons, electrons, and from K to here, do with pencil, so you can keep on redoing it till you understand properly. Okay. What is valency? I'll explain it in terms of practical application, which is easier to understand. Instead of definition for now, we'll do the definition later on. Okay. Now here. Now helium is perfect. 2. See here, 2 electrons in first shell, like that it is perfect. So noble, look at these 2 noble gas, helium and neon. But hydrogen is only 1, so it's not perfect. So because it's not perfect, it always has the desire to become like the perfect fellow helium. Just like many boys want to be like, let us say, a superstar, let us say, or Ronaldo. Okay, every boy who likes football, let us say, want to be like, play like, means Ronaldo is a perfect model, something like a perfection they want to reach, right? Similarly, here, hydrogen is like that boy who wants to be like Ronaldo. So the helium is here like the perfect one, Ronaldo. So every hydrogen wants to become perfect like helium. So to do that, it needs 1 more electron, right? To satisfy this 1 plus 1, then become 2. So how much electron does it need to become like helium? 1 more. It just 1 more, and it'll become perfect. 1 plus 1, 2, like the noble gas helium. So remember, hydrogen always tries to attain the electron distribution of helium, which is perfect. So to do that, it needs 1 more. So that is called valency. The number of electrons needed for hydrogen to become perfect like helium, which is 1 in this case, is called its valency. The number of electrons needed by an element which is not noble to become like a noble gas, noble element, is called its valency. So 1. Now here, helium has perfect arrangement 2. Maximum in the first shell 2, and exactly 2 it has, and no more electrons, so perfect arrangement. So this perfect arrangement where in the first shell the element helium has perfect 2 electrons is called duplet arrangement, duplet perfect arrangement. Okay, duplet means 2. So you don't need any more electrons to become perfect. It is already perfect. So it doesn't need any extra electrons, or it doesn't need to give away also. So valency doesn't need any help from any electrons, so 0. Already perfect means valency is 0. So in other words, valency means the number of electrons needed to make that element perfect like a noble gas. Now here, lithium. Lithium has got perfect 2 in the first one, but second one is not perfect. So lithium here, to become perfect, second shell perfect is 8. So to become perfect, it needs 7 in the second shell, then 7 plus 1, 8, then 2, 8, it will become perfect. 2, 8 like neon. But that is too far. To ask 7 from electrons from others is too difficult. So easier way is give away. So minus. So it will say, if I give away my second shell electron, give away 1 to somebody. Okay, let me just rub out. Don't rub out, okay, like this. Then I will become like helium. So difference, both of them, hydrogen and lithium, both wants to be like the noble gas helium. But hydrogen does it by taking 1 more from others, so 1 valency plus 1. But lithium do the opposite. Hydrogen take 1 to become 2, 1 plus 1, 2. But lithium give away 1 in the L shell to become 2 in the K, just like helium. So give away. Both of them want to be like helium. But by a method by which hydrogen and lithium achieve that is exact opposite to each other. Hydrogen take 1 electron to become like helium, 1 plus 1, 2. Lithium give away 1 electron from L shell to become like helium, 2 in the K shell. So valency is same. So valency, in other words, means number of electrons that an element need to become like a noble gas, noble element, or the number of electrons it needs to give away also to become like a noble gas. Next here, lithium. So here, beryllium here, 2 and 2. So here, to become perfect like helium, all these here, hydrogen, lithium, beryllium, all of them will try to become like helium, okay, because it's nearer to helium than to the next noble gas. Here, neon. Neon is too far from hydrogen, lithium, beryllium, so all of these will try to become like helium. So helium is like the Ronaldo to them, wanting to be perfect. So lithium here, 1 giveaway. Beryllium will give away this 2. Give it to others. Then it will become 2 like helium by giving away 2. So giving away 2 to become like a perfect gas. So 2 is the valency. Then boron, it give away 3. Then 3 minus, then it will become exactly like helium. So that's why valency is 3. Okay. Then carbon here. Carbon is of here, see. Carbon, it doesn't give away also, take also. But see here, to become perfect, it needs 4 more. So these are all take, give away, give away, give away. But valency also, the number of electrons taken or given away to become like a noble gas. Or another definition for valency is the number of electrons it can share. Okay, so here carbon is characteristic property here is that it shares to become like noble gas. So it will here share from carbon here, from up to here, boron, beryllium, lithium, helium, hydrogen. All this will want to become like helium. But carbon to here, fluorine, they will all try to become like the next noble gas. So in order for carbon to become like the next one, it needs 4 more electrons, 4 plus 4, then 8 like this. So to become like neon, instead of giving away or taking, it will share. As we go to the next 3rd or 4th class, you will clearly understand this carbon case. Okay, so here, it will share 4. It will give 4 and tell others also to give 4. So others give 4. It will give 4 to others and tell others, I'm giving 4, so you also give 4. So it will become 8. Others will give 4. It will give 4. Means in other words, carbon will share 4 and it will ask others also to share. Share means this 4 of carbon shared and 4 of others shared will become common property for those 2, carbon and that element, to make it 8. So sharing 4, it needs to share 4, so its valency is 4. Then here oxygen, 2 and 6 plus 2, then it will become 8, just like neon. So it will take, here not share, okay, it will take 2 from others. It will take 2, or or it can take 2 from others, or it can also share also both, but it needs 2 anyway. So there is plus 2, then become 8, perfect like neon. So its valency is 2. Nitrogen, sorry, I went one step ahead. Nitrogen here 5, sorry, 5. So it needs 3 more. 5 plus 3, 8 to become 8. So plus 3, right? Plus 3 means it will take 3 from others, or it can also share. Both it can do, and so it will become 3 is the valency of therefore nitrogen. Then here, to become like neon, oxygen has to take 2 or share 2 with others, then become 6 plus 2, 8. So it will valency is 2, because 2 is deficient. Here 2, 7, 1 deficient. Only 1 more needed, then become 8. So valency is 1. And then neon, it's already perfect arrangement. First shell perfect is 2 electrons, second is 8. So here first shell K2, second shell L8, perfect arrangement. So it doesn't need any electrons from others, nor does it need to give away. So valency, if it's perfect, as I said, is 0. So all noble gases have valency 0, but because they do not require any more electrons from others, nor do they need to give to others to become perfect. They're already perfect, therefore their valency is 0. So in other words, valency is the number of electrons that an element needs to take, or needs to give away, or needs to share. Take, give, or share to become perfect electron arrangement is called valency. That is a simple language explanation of valency. I hope this class is not too long. Next 10 elements, already 10 here. The next 10 we'll do in the next class. This is activity. You can write your activity, okay? This table, just above this table. Okay.